Okay, so this is 7.3 Einstein's photoelectric theory. Okay, so this Einstein photoelectric theory is based on the photoelectric effect lah. Okay, all right. So let's look at Einstein photoelectric theory. Okay, Einstein applied Max Planck's idea of energy quantum. He suggested that energy is carried by light particle called photon. Energy of each photon is directly proportional to the frequency of light and can be determined by the following equation. Okay, so this is something that we already learned in 7.1. Okay, in 7.1. Alright, so that means the greater the frequency, the greater the frequency of light, the greater the energy of the photon. Okay, the greater the energy that is contained within each photon. All right, so that means for example, we have the electromagnetic wave. There are a lot of type of electromagnetic wave, right? From radio wave to microwave to infrared to visible light to ultraviolet to X-ray to gamma ray. So that means the photon of radio wave, because the frequency is very low, so the photon of radio wave have very low energy. Okay, so we have photon of radio wave. Okay, radio wave photon, so the energy will be super low lah. Okay, very low, because the frequency of the radio wave is very low, so the energy inside the photon of radio wave is very low. So that means the photon of microwave, which have a higher frequency, will have higher energy, and the photon of infrared will have higher energy than microwave. Visible light photon, okay, will have higher energy than infrared. Okay, ultraviolet have higher energy than visible light. X-ray have higher energy than ultraviolet, and gamma ray will have the most energy lah. Okay, the photon of gamma ray have the most amount of energy because the frequency of gamma ray is the highest among all of the type of electromagnetic wave. Okay, all right. So each quantum of light is a discrete packet of energy. There are many energy packets in a beam of light that shine on the metal surface. When a photon arrives at the metal surface, the photon energy will be fully absorbed by an electron in the metal. This energy is used to release the electron from the metal, and extra energy will become kinetic energy of the photoelectron. Okay, usually the electron on the metal surface will acquire maximum kinetic energy compared to the electron inside the metal. So that means basically what is said here is that the photon, okay, previously we got learned about threshold frequency, right now? Okay, threshold frequency. Okay, threshold frequency. Okay, so different metal, they have different threshold frequency. For example, iron have its own threshold frequency, copper have its own threshold frequency, aluminium have its own threshold frequency, sodium have its own threshold frequency, magnesium have its own, and so on. Okay, every different metal, they have their own threshold frequency. So some threshold frequency is higher, some threshold frequency is lower. So what is threshold frequency? Threshold frequency is the minimum frequency of the photon that can make the electron of the metal to escape. Okay, that can supply enough energy to the electron of the metal to escape, and that means produce a photoelectric effect. Okay, so for example, this is thallium. Okay, This is thallium. So the threshold frequency of thallium is 1.03 times 10 power by 14 hertz. Okay, 1.03 times 10 power by 14 hertz. So that means the frequency of photon that can make thallium, okay, the metal thallium to have photoelectric effect is the photon must have the frequency of 1.03 times 10 power by 14 hertz. Okay, then only the photon have enough energy to make the electron of thallium escape and become photoelectron. Next is this one. This one is titanium. Okay, so the threshold frequency of titanium is 1.05 times 10 power by 14 hertz. Okay, so that means the minimum frequency of photon that can make the titanium have photoelectric effect is 1.05 times 10 power by 14 hertz. Okay, this is molybdenum, this is aurum, this is lead, this is if I'm not mistaken, is iridium. This is it platinum? I think. Okay. Yeah, I think this is platinum. Okay, platinum. Okay. So you see, different type of metal, they have their own threshold frequency. Okay, they have their own threshold frequency. And the frequency range of visible light, visible light. Okay, visible light, the frequency range is around 4 times 10 power by 14 hertz. Okay, 14 hertz to 8 times 10 power by 14 hertz. So as you can see, the threshold frequency is 1.03. Okay, 1.03 times 10 power by 14 hertz. So okay, so from this range of frequency of visible light, so we can see that the threshold frequency of this metal, okay, is only 1.03 to 1.36 times 10 power by 14 hertz. So that means if we have visible light, if we shine visible light onto this metal, then this visible light the photon of this visible light will have enough energy to make the electron of this metal to escape. That means it can cause this metal to have photoelectric effect. Okay, so for example, let's say that we use light with a frequency of 4 times 10 power by 14 hertz. Okay, 4 times 10 power by 14 hertz is most probably is red light, okay, red color light. So this red color light, okay, red light, okay, we shine this red color light onto the metal thallium. Okay, so you see this red color light have a much higher frequency than the threshold frequency. That means the photon of the red light actually have more than enough energy to make the electron escape from the surface of thallium. Okay, from the surface of thallium. So what happened to the extra energy? The extra energy of the photon, okay, because the energy is more than enough, right? Not more than enough, because the frequency is more than the threshold frequency. So the extra energy will become the kinetic energy of the photoelectron. Understand? So basically, the photon, if the photon have enough, if the photon have more have higher frequency than the threshold frequency, then the extra energy will be able to make the electron to have kinetic energy. Okay, so the higher the frequency of the photon, the greater the kinetic energy of the photoelectron. So we can see from this equation. Okay, so the photon, okay, for electron on metal surface, for electron on the metal surface, photon energy will be equal to the minimum energy required to release a photoelectron plus maximum kinetic energy of photoelectron. That means if the photon have more than enough energy, then the extra energy will be able to give the photoelectron kinetic energy. Okay, so E is the symbol for photon energy, the energy of photon. So this W is the minimum energy required to release photoelectron, and this is K max is the maximum kinetic energy of a photoelectron. So why is it that we use a symbol of W? Because W stands for work done. That means in order for the electron to escape the surface of the metal, it needs to do work against the resistance force, okay, the forces that pull the electron, or the forces that hold on to the electron to the surface of the metal. So the electron need energy to do work against the forces that bind the electron on the metal surface. So we use W as the minimum energy, or the minimum work done, or the work that need to be done to make the electron escape. Okay, so the photon energy, so from E equals to Planck constant times the frequency of the photon. So we can substitute E, the photon energy, with HF. Okay, Planck constant times the frequency of the photon. So equals to W plus half mv square. So half mv square is the equation for kinetic energy. Okay, this is something that you learn in Form 3, if I'm not mistaken. Okay, science Form 3. So the kinetic energy, okay, the kinetic energy will be equals to half mv square. V is the mass, m is the mass of the object, and v is the velocity of the object. So the maximum kinetic energy will be able to give the photoelectron the maximum velocity. Okay, the maximum velocity of the photoelectron that the photoelectron can have from this amount of kinetic energy. Okay, so rearranging the equation, so we can get that the kinetic energy, okay, the maximum kinetic energy that the photoelectron can have will be equal to the difference in the amount of energy in photon and the minimum energy needed to release the photoelectron. So this is the equation of the, okay, this is the equation of the Einstein's photoelectric theory. Okay, that means Einstein photoelectric theory is actually to find the maximum kinetic energy of the photoelectron. Okay, so that is why when we want to explain what is Einstein, or the equation that is related to Einstein photoelectric theory, this is the equation. Okay, the equation that shows us how to get the maximum kinetic energy of photoelectron. Okay. So Einstein's photoelectric equation. So this is Einstein's photoelectric equation. Is in accordance with the principle of conservation of energy. That means the energy from the photon that is absorbed by the electron, the extra energy will not disappear. That means a part of the energy is used to release the electron from the surface, and the extra energy will turn into the kinetic energy of the photoelectron. So that means no energy is lost. That means we know the energy go to where. Okay, we know what happened to the energy. So this is in accordance with principle of conservation of energy. So if you remember, principle of conservation of energy is where we say that energy cannot be created or destroyed. It can only be converted from one form to another. Okay. Okay, so at the threshold frequency, photoelectrons are emitted without any kinetic energy. So that means if the photon, the frequency of the photon is exactly the threshold frequency. Let's say okay, if the frequency of the photon is exactly the threshold frequency of the metal, then that means when the electron absorb the energy from the photon, although the electron have enough energy to escape the surface, but the electron do not have kinetic energy because there's no extra energy to convert into kinetic energy. So at threshold frequency, the kinetic energy will be 0. Okay, get the idea? Because this is the energy of the photon. This is the energy needed to escape the surface. So if the photon have the frequency of threshold frequency, that means the energy of the photon will be equal to the energy that is needed to escape the surface. So this energy minus this energy, then will be 0. So that means you will have no kinetic energy. Okay, so if there is no kinetic energy, so that means this so the Planck constant times the threshold frequency minus the work done, that means minus the minimum energy needed. So this minimum energy needed will be equal to the Planck constant times the threshold frequency. So this is how we calculate the minimum amount of energy that is needed. Okay, the minimum amount of energy that is needed to for the electron to escape. Okay, that means the minimum amount of energy of the photon to have photoelectric effect. All right. So this W, okay, this is called the work function. Okay, this is called the work function. So basically, the work function is the minimum work done. Okay, the work done to for the electron to escape the surface of the metal. Okay, so we call it the work function. Alright, so if we substitute this work function into half mv square equals to hf minus w, so we get the equation like this. So we can factorize the Planck constant out, and then we will see that this is the difference in the frequency of the photon. Okay, that means this is the frequency of the photon that is absorbed. Okay, frequency of the photon that is absorbed by the electron minus the threshold frequency. So this difference in frequency will be able to give the photoelectron kinetic energy. Okay, get the idea. So if there is a difference in the frequency of the photon, that means if the difference is positive, then that means the photoelectron will have kinetic energy. If this minus this is 0, that means the frequency is the same, then there will be no kinetic energy. And if the frequency, if this minus this, you get negative number, that means the frequency of the photon is smaller than the threshold frequency. That means not only you don't have kinetic energy, but the electron don't even have enough energy to escape the surface. That means no photoelectric effect. Okay, so work function and threshold frequency for photoelectric effect. Okay, so the minimum energy required for photoelectron to be emitted from a metal surface is known as the work function. Okay, so we already learned how to calculate the work function just now. Okay, so W, the work function, will be equal to the Planck constant times the threshold frequency of the metal. Okay, threshold frequency of the metal. Alright, so the minimum frequency for a light photon to produce photoelectric effect is called threshold frequency. So this one, threshold frequency. Okay, so the relationship between maximum kinetic energy of photoelectron and the light frequency is shown by graph in figure 7.12. The graph is a straight line with a positive gradient and not passing through the origin. The threshold frequency is the value of the intercept on the frequency axis. Okay, so you see this graph. Okay, this is a graph of kinetic energy of the photoelectron against the frequency of the photon. Okay, this is the frequency of the photon. So that means if the frequency of the photon is less than the threshold frequency, then there will be no photoelectric effect. Okay, that means this side is no photoelectric effect because the energy of the photon is not enough to make the electron escape the surface. Okay, because the frequency is less than threshold frequency, so the photon don't have enough energy. And when the frequency of the photon is exactly the threshold frequency, the electron can escape the surface, but the electron do not have kinetic energy. That's why you see at the threshold frequency, the kinetic energy of the photoelectron is 0. Okay, is 0. So the photoelectron will only have kinetic energy when the frequency of the photon is greater than the threshold frequency, so that the photon will be able to supply not only have enough energy for the electron to escape the surface, but have extra energy that can be converted into kinetic energy of the photoelectron. Okay, actually this is the same thing as what we already discussed. Okay, what we already discussed just now. Okay, so the relationship between work function and threshold frequency of a metal can be determined by the relationship W equals to HF. Okay, so photoelectron will acquire kinetic energy when light frequency exceeds, that means more than threshold frequency. The higher the threshold frequency of a metal, the higher the work function. That means if the threshold frequency of metal higher, that means the electron will need to do more work in order to escape. So this will make the work function to be higher. Okay. So this means the minimum energy required for photoelectric effect to occur is higher. So as what you can see, the work function equals to the Planck constant times the threshold frequency. So if the threshold frequency of the metal increase, so the work function will increase also. Okay. So different metal have different threshold frequency as shown in figure 7.13. So for example, here we have different metal. Okay, metal A, B, and C. So these different metal, they have different threshold frequency. Okay, so for example, metal A, they have smaller threshold frequency. B have higher, C even higher lah. Okay, like that. Okay, so to observe threshold frequency of different metals, so you can scan this or type in this link, okay, to watch the simulation. Okay, so the activity 7.8 to determine work function of metal using a formula. So the formula to find the work function is this. Work function equals to the Planck constant times the threshold frequency. So here you see you have different type of metal, like what we discussed just now, thallium, titanium, molybdenum, aurum, plumbum, iridium, I think, and platinum. So they have different threshold frequency, and we can calculate the work function of these different metal just by using the equation of W equals to, the work function equals to Planck constant times the threshold frequency. So for example, we want to calculate the work function of thallium. Okay, so W equals to H times the threshold frequency. So the Planck constant 6.63 times 10 power by negative 34 times the threshold frequency 1.03 times 10 power by 14 hertz. Okay, so we will be able to get 6.83 times 10 power by negative 20 joule. Okay, 6.83 times 10 power by negative 20 joule. So this is the minimum energy needed to dislodge the electron, or to make the electron be able to escape the surface of the metal of thallium. Okay, so the work function is 6.83 times 10 power by negative 20 volts. Negative 20. Alright. And let's try to calculate for platinum. Okay, so Planck constant 6.63 times 10 power by negative 34. Okay, work function 1.36. Threshold frequency 1.36 times 10 power by 14. So we get 9.02 times 10 power by negative 20 joule. Okay, so 9.02 times 10 power by negative 20. Okay, negative 20 joule. Alright. So from here we can see that as the threshold frequency increase, so the work function will also increase. That means more energy is needed to make the photoelectric effect happen. Okay, let's look at some example. Problem solving using Einstein's photoelectric equation. Okay, so here it says that a blue light with frequency of 6.67 times 10 power by 14 Hz is shown on a plain cesium metal surface. What is the maximum kinetic energy of photoelectron emitted? Okay, so we want to calculate the maximum kinetic energy. So the maximum kinetic energy can be calculated by taking the energy needed for the energy that the electron, the energy of the photon, energy of the photon minus the work function, minus the work function. Okay, or easier is I think we start with equation that we familiar lah. Okay, equation that we familiar. So that means the energy of the photon. No. Okay, I think better to use the equation for the Einstein photoelectric theory lah. Okay, so the kinetic energy maximum will be equal to the energy of the energy for the photon minus the work function. Okay, all right. So you can use this also, or you just write W also can. Okay, W also can. All right. So this is the energy of the photon. So the Planck constant 6.63 times 10 power by negative 34 times the frequency of the light 6.67 times 10 power by 14 minus the work function 3.43 times 10 power by negative 19 joule. Okay, so equal to, and we can get maximum kinetic energy 9.92 times 10 power by negative 20 joule. Okay. Okay, next figure 7.14 show the change in kinetic energy of photoelectron released from lithium for different light frequency. Okay, determine the threshold frequency from the graph and calculate work function of lithium. Okay, so first is determine threshold frequency. So the threshold frequency we can see from the graph. Okay, you see, so this is the minimum frequency that can make the electron escape. So that means here, over here, this is the threshold frequency. Okay, so we can see that it is 5.6. Okay, 5.6. Okay, so from the graph, the threshold frequency is 5.6 times 10 power by 14 hertz. Okay. Alright, calculate the work function of lithium. So the work function can be calculated by taking the Planck constant times the threshold frequency. Planck constant 6.63 times 10 power by negative 34 times the threshold frequency 5.6 times 10 power by 14. So we can get we will be able to get 3.71 times 10 power by negative 19 joule. Okay, so this is the work function of lithium. Okay, next, what is the maximum velocity of the photoelectron emitted when a monochromatic light with wavelength of 550 nanometer is shown on a metal which has a work function of 2 electron volt. Okay, 2 electron volt. Electron volt is the unit for energy also. Okay, electron volt is unit for energy. Because from the equation or from the definition of voltage equals to work done for every unit charge to move from one point to another point in an electric field. Okay, the work done for every unit charge to move from one point to another point. So the charge here is the charge of one electron. So we substitute with the equation of with the symbol of a small e. Okay, so W is the energy. Okay, or the work function. So you can see that we can take the voltage times the charge of one electron. So that means the unit, this work is this energy, right? So that means the unit of this energy, it can be electron volt lah. Okay, this electron volt. This V is a unit, is a unit. The symbol for, please don't get confused. This V is potential difference or voltage. This V refers to the symbol of unit volt. Okay, so this E we read as electron. That means the charge of one electron. Okay, the charge of one electron times the how many volt. Okay, how many volt that is supplied. Then we get the amount of energy that is obtained by that one single electron. Okay, so 2 electron volt basically means the charge of one single electron get the energy from the amount of energy that is 2 volt. Okay, get the amount of energy from 2 volt like that. So 2 electron volt. Alright, so in order to convert the electron volt into joule, then we can use this information that is given. So 1 electron volt equals 1.6 times 10 power by negative 19 joule. Okay, so in SPM, I believe this information will be given either in the question or in the formula list. Okay, in front of the question paper, you have formula list. So make sure you look through the formula list. Okay, for any constant number or information that you will need. Okay, so don't worry, you don't have to memorize. Okay, for example, mass of electron, Planck constant, all of this constant number you do not have to memorize. Okay, don't worry about that. Alright, so we want to calculate the maximum velocity of photoelectron. Okay, emitted. Okay, so we want to calculate the maximum velocity, so we need the kinetic energy. Okay, kinetic energy maximum, so equal to the energy of one photon minus the work function. Okay, so the maximum kinetic energy is half mv max square. Okay, maximum velocity square. Okay, so hf minus the work function. Alright, so half mv max square equal to, okay, this frequency here is a frequency of the photon, or the frequency of the light. But in this question, it doesn't give us the frequency of the light. Instead, the question gives us the wavelength of the light. Okay, the question gives us the wavelength. So we can use the wavelength to calculate for the frequency. Okay, so from the equation of C equals to F lambda, C is the speed of light, F is the frequency of the light, lambda is the wavelength of the light. So the frequency equals to the speed of light over the wavelength of the light. Okay, so H C over lambda minus the work function. So now we can put in all the information. So half mass of the electron 9.11 times 10 power by negative 31. okay, V max squared. So equals to Planck constant 6.63 times 10 power by negative 34 times the speed of light. In this question they give us Hc is equal to 1.243 times 10 power by 3. So that means this Hc here, the value of Planck constant times the speed of light already given, okay, Hc. So this is 1.243 times 10 power by 3 electron volt nanometer over the wavelength. Okay, so the wavelength is 550 nanometer, and you see that here the unit that is given for Hc is already in nanometer. So that means you don't convert it into meter. You just write 550. Okay? You don't write 550 times 10 power by negative 9. Okay? No need to convert the 550 nanometer into meter. The reason is because everything inside here, we need it to be in the same unit. Okay, we need it to be in the same unit. So this is nanometer. So this one also we put 550 nanometer. Okay, so the nano at the top here, the nanometer, and the nano at the top here, and the nano at the bottom here, they will be able to cancel each other off. Okay, when we calculate it will automatically cancel each other off, because nano represent the value of 10 power by negative 9. So at the top got nano, at the bottom also got nano. That means at the top got 10 power by negative 9, at the bottom also got 10 power by negative 9. So it will divide and become 1. Okay, we cancel each other off. So we do not need to put 550 times 10 power by negative 9. Okay. So minus the work function. Okay, so the work function here we need to convert it into joule. So we take 1 electron volt is 1.6 times 10 power by negative 19 joule. So it's 2 electron volt. So that means 2 times 1.6 times 10 power by negative 19 joule. Okay. So solve this, we will be able to get the maximum velocity. Okay, wait, got mistake. Got mistake here. We need to put times 10 power by negative 9 after all. Okay, we need to put, because this one is in the unit of electron volt nanometer. Okay. So the electron volt already take into account the nano. Okay, already take into account the nano. So we still need to put the nano at the bottom here. Okay. Okay, sorry, mistake. Okay, actually here don't have 10 power by negative 9, and actually this one don't need to times 2. Okay, don't need to change into joule. Okay, if we are using this value that they give us, okay, if they use the value that they give us, then we do not have to change into joule. So just minus is 2 electron volt. Okay, so just minus 2. Alright, because this one because this is like this, because the value of this Hc, okay, equal to 1.243 times 10 power by 3 electron volt nanometer. Okay, so when we take this, so the energy of photon is Planck constant times the frequency, and frequency can substitute with speed of light over the wavelength. So if we take this value of Hc, okay, 1.243 times 10 power by 3, electron volt per nanometer divided by the wavelength, which is 550 nanometer. Then we will be able to get the value after we divide. Then the value it will be in electron volt. Okay, that means the answer will be in electron volt. So that means the result here can straight away minus by 2 electron volt. Okay, so we solve this. Oh, and this whole thing, because this whole thing is in electron volt, so that means we have to change it into joule first. Okay, we have to change it into joule because this half mv square is where we calculate the half mv square. We calculate the energy, the kinetic energy in the unit of joule. So that means this is in electron volt. So must convert into joule. So that means this electron volt, how many electron volt must times 1.6 times 10 power by negative 19. Okay, and we will be able to get 302205.6. Okay, 0.6 meter per second. Okay, meter per second. Okay, next, when a photocell is shown on with a red light, okay, wavelength equals to 750 nanometer, and then with a blue light with a wavelength of 460 nanometer, the maximum kinetic energy of the photoelectric emitted by the blue light is 2 times that of the red light. So what is the work function of the photoelectric material in the photocell? Okay, so for this one, we want to find out the maximum, or we want to find out the work function. We want to find out the work function of the photoelectric material. So we know that when shine with red light, when shine with blue light, the maximum kinetic energy of photoelectron will be double. Okay, 2 times of the red light. Okay, so we need to build two equation. Okay, we need to build two equation. Okay, so first is, alright, so the energy of the photon equal to the work function plus the maximum kinetic energy. So this energy, energy of photon, we can write as the Planck constant times the speed of light over the wavelength of the light. Okay, why we use the wavelength instead of the Planck constant times frequency? Because in this question they give us the wavelength. Okay, so equals to the work function of the material plus the maximum kinetic energy. Okay, so for the first, okay, for red light, okay, for red light, the Planck constant is 6.63 times 10 power by negative 34 times speed of light is 3 times 10 power by 8. Okay, divide by the wavelength is 750 nano. Okay, negative 9. Alright, so equals to the work function plus the maximum kinetic energy. Okay, now for the blue light. Okay, for the blue light, same thing also, 6.63 times 10 power by negative 34, 3 times 10 power by 8, and the wavelength is 460 times 10 power by negative 9. But this time, okay, work function is the same, W, but now the maximum kinetic energy is 2 times of K max. That means double of this one. Okay? So, okay, so for red light, we get 2.652 times 10 power by negative 19. Okay, and for blue light, we get 4.324, okay, times 10 power by negative 19. Okay, so we only want the work function, so we want to remove the maximum kinetic energy. Okay, we want to remove the maximum kinetic energy, so this one times 2. Okay, times 2, so then both will have 2 K max. Okay, this one times 2. This one times 2. Okay, so we get, okay, so this one will be 5.304 times 10 power by negative 19 equals to 2W plus 2K max. Okay, so let's say, okay, this is equation 1. This is equation 2. So we take equation 1 minus equation 2. And we can get 5.304 times 10 power by negative 19 minus 4.324 times 10 power by negative 19 equal to, okay, 2W plus 2K max minus W plus 2K max. Okay, so we get, okay, this side is 0.98 times 10 power by negative 19. This side is 2W minus W, so get W, so 2K max minus 2K max, so gone. So that means the work function will be equal to 9.8 times 10 power by negative 20 joule. Okay, so this is part A. Okay, part B, what is the threshold wavelength of the photoelectric material? Okay, B. Okay, so we have the work function. We want to find the threshold wavelength. So from work function is equals to the Planck constant times the threshold frequency. So we can get that the threshold frequency is equal to the speed of light over, this is speed of light, over the threshold wavelength. Okay, so threshold frequency, then the opposite, okay, it will be threshold wavelength, okay, like that. So that means that is C equals to F lambda. So if this frequency is a threshold frequency, then this wavelength is a threshold wavelength. Alright, so so we can get 9.8 times 10 power by negative 20. This is 6.63 times 10 power by negative 34. Speed of light 3 times 10 power by 8. threshold wavelength. So threshold wavelength equal to, okay, so we can get 2.03 times 10 power by negative 6 meter. Okay, so this is the threshold wavelength. Okay, continue. Generating photoelectric current in a photocell circuit. Okay, so we look at this circuit. So this circuit already have a power source, and then we can see that this is a photocell. So this photocell can act like a switch, like that, light activated switch. So you can see that this terminal, this anode is connected to the positive. This cathode is connected to the negative. Okay, so under normal condition, okay, that means when there's no light, then the milliammeter will show 0 reading, okay, no current. But when there's light shine on the cathode, then the light can produce photoelectric effect. Okay, so because have photoelectric effect, so the electron will bridge the gap between the cathode and the anode, so current can pass through the photocell. So the ammeter, the milliammeter will show a reading. So that means got light, then got current. No light, no current. Alright. So figure 7.15 show a photocell circuit consisting of a glass vacuum tube. The semi-cylindrical cathode is coated with a light-sensitive metal and connected to the negative potential. Okay, the anode is a metal rod fixed at the axis of the semi-cylindrical cathode and connected to the positive potential. When the photocell is illuminated by light, the production of photoelectric current is produced in the circuit. So table 7.5, two example of common photocell. Okay, so we look at here, we have one that is made from cesium, another made from lithium. Okay, so the work function of cesium is 2.14 electron volt. Work function of lithium is 2.5 electron volt. So the threshold frequency for cesium is 5.16 times 10 power by 14. Lithium is higher, 6.03. Okay, so that means the maximum wavelength to produce photoelectric current is 579 nanometer, while lithium is 496 nanometer. Okay, so this is just example lah. Okay, example of photocell that is made from cesium and lithium. So that means we can see that cesium and lithium will be activated by different light. Okay, different light. Cesium need that means the energy that is needed to activate the cesium is lower because of the lower threshold frequency. Okay, so that means it's easier to activate the cesium than the lithium lah. Okay, photocell. Okay, on the whole, the higher the work function, the shorter the maximum wavelength required to produce photoelectric current. So as the light intensity increase, the photoelectric current in the photocell circuit also increase. Okay, so this is light intensity and photoelectric current. Okay, that means this is the current, not the kinetic energy of the photoelectron. Okay, the reason is because if the light intensity increase, that means you have more photon. Number of photon increase. So if the number of photon increase, that means the number of photoelectron also increase. So you have more photoelectron, that means you can the current the charge that pass through the photocell is higher lah. Okay, higher current because more charge can pass through at the same time. So that means higher current. Okay, remember current is charge per unit time. That means every 1 second how much charge can pass through. So if you have more photon, you have more photoelectron. So that means every 1 second more charge can pass through. So if more charge can pass through, then the photoelectric current increase lah. Okay. So please do not confuse this with previous what we talked about is the light intensity. Okay, do not affect the kinetic energy of photoelectron. That means greater light intensity can increase the number of photoelectron, but the kinetic energy of photoelectron no effect. Okay, one more time. Greater light intensity, more photoelectron, but photoelectron kinetic energy no increase. The only way that we can increase the kinetic energy of photoelectron is by increasing the frequency of the light. That means you increase the frequency of the light, that means the photon of the light have more energy, then the photoelectron have more energy, that means the photoelectron will have more kinetic energy. Okay? Alright. Okay, so that is all for Einstein photoelectric theory. And after this is just the application, so you can read the application in the textbook and also in the note. The note also take from the textbook lah. Okay. So for the example, you don't have to like actually understand how it works. You only need to know that okay, photoelectric effect we can apply this in this field, this thing, use photoelectric effect. Okay, you don't need to like actually know in detail how it works.